In this video, we're going to discuss the concept of pushforward, which is kind of a generalization of change of coordinates in linear algebra. So in linear algebra, recall that vectors are written in different ways in different coordinate systems. And in our world, a function from one manifold to another can kind of be thought of sort of as putting coordinates from the first manifold onto the second one. So the idea of pushforward is sort of extending this change of coordinates idea to more general manifolds, and maybe even to just, subsets, manifolds which are subsets of other manifolds, not necessarily changing coordinates on the whole manifold. Okay, so how is this going to work? So recall that if f is a function from Rn to Rm, then it has a derivative, df, and df at each point P is a function also from Rn to Rm, but it's linear. It's a linear map. So is there a better way to package up all of the df at P's for every point? Yes, there is, using the tangent bundle. So how are we going to do this? So if I write f as f1 through fn, then the ith column of df at P is precisely dfi at P, right? And dfi at P is a linear map from TPRn to Rn, just to R. And really, what I should be thinking of is I should secretly be thinking of this R as identified with the tangent space to fi at P, tangent space at fi of P to R. Because if I do this, then when I sort of stack up all of these maps into my Jacobian matrix, what I really should be thinking of as my Jacobian matrix should really eat points in vectors in TPRn, just like all of these DFIs do, all of its rows do, and should really spit out something in the tangent space to f of P of Rm, because there are m of these rows. So that's how I can sort of think about changing coordinates on each tangent space all together. So let's think about this as an example. If I have f being polar coordinates, I'll set this aside, say example. So if f is polar coordinates, so f goes from R2 with coordinates r theta to R2 with coordinates x, y, and it's our standard polar coordinate map that we know and love. So r theta goes to r cosine theta, r sine theta. Then when I actually write df as a matrix at the point r theta, what I should do is take in the first column the derivatives of each entry in the r direction. So it should be cosine theta, sine theta. And then the second column is in the theta direction. So negative r sine theta, r cosine theta. And notice that the first row is basically just the differential of sort of this x function, and the differential of the second row is the differential of the y function. So here I'm calling x my f1 and y is my f2. And if I want to visualize sort of what df is doing, I'm going to draw myself, so I'll give myself a little more space. So here's my df. If I draw, so I'm drawing on the xy plane. I want to draw lines of constant r. So here's r equals 0. Maybe I can think of that circle as r equals 1, r equals 2, pardon my poor drawing. And then I'll draw lines of constant theta. So maybe theta equals pi over 4, theta equals 5 pi over 6, etc. Random values of theta. So these would be constant values of theta. And if I want to actually compute, so if I want to compute what df does to vectors in each of these points, it will do a different thing to vectors at different points. So I kind I was a little bit misleading adding this point in. This point should not really be here. So I'll draw a little empty circle to show that shouldn't be there because that's not in the image of f. Because I should really be thinking of f. I mean, it is in the image of f, but it's a little bit confusing. It's sort of the point that messes up f being 1-to-1. So now I can think about what df, let's do df at 1, 0, applied to the vector d by dr is. Well, this should just be cosine theta d by dx plus sine theta d by dy, and theta here is 0, so cosine theta is 1, and sine theta is 0, so I get no d by dy's. So when I draw the image of this vector, let's draw it in pink, say. So that's this. This is just sort of 1 unit going that way, and I'm centering it. I'm starting it at the point 1, 0 in our theta coordinates, which turns out to be 1, 0 in xy coordinates. But we'll see some points where that's not the case. So let's do df at 1, 0 of d by d theta. So this is the second column, so minus r cosine theta d by dx plus r sine theta d by dy. So this will be cosine theta will be 1, and r is 0, so this will be, or sorry, r is 1, so this will be negative d by dx. And then sine theta is 0, so no d by dy's. So df at 1, 0 of d by d, oh sorry, I mixed, yeah, I was like, why is this happening? This can't be right. I mixed these two up. Sorry, this should be sine, and this should be cosine. Yeah, that's correct. So right, so then I get no d by dx's, and I just get a d by dy. And I'll do this one. No, I already used orange. I'll use purple here. So this is this vector. But now let's compute what these are at different points. So let's do, say, df at 0, 1, d by dr. This is going to be, let's not do 1, sorry, let's do pi over 2. So then cosine of pi over 2 is 0, but sine of pi over 2 is 1, so this is d by dy. And I will do this one in dark green. So that will go, actually no, sorry, I'll do it in pink again. And the reason why is that you'll then end up sort of seeing where the vector d by dr goes at different, when I change r and theta. So this turns into d by dy. So I was at 0 pi, or 1, I don't want to be at 0, I want to be at 1. Sorry, 1 pi over 2. The first column doesn't depend on r, so it doesn't matter. So I want to be here. And then I'll just do this whole next part in purple. df at 1 pi over 2 of d by d theta is equal to, so now plugging into here, r equals 1, so I get negative d by dx. So then this is right here. And you can see, what you'll see in general is that d by d theta is going to end up being tangent to this circle, and d by dr is going to point perpendicular to it. And then the scale of d by dr will not change, but the scale of d by d theta will, because of this r. So when I go out here, for example, I'll have same length 1, that's maybe a little too long, same length 1 d by dr, but now d by d theta is going to be longer. Something like that. And also, just so you know, in section 6.1 and 6.2 of your book, Fortney does a linear example where f is linear. So this matrix actually looks a lot like the actual function f. So maybe a simpler example where the directions and the sizes of these vectors don't vary at all when you vary the point. So the story generalizes. So if F is a map from one manifold M to a manifold N, then we get the derivative of F at P goes from the tangent space at P to M to the tangent space at F of P to N. And there's also some other notations that we use for dfp. We sometimes use df at P. We use T sub P of F. We'll also use D at P of F. And we might also use, the one that I commonly use is F sub star, which we call F push forward. And the way I define this map, F push forward of a vector at in the tangent space to M at P is just compose df at P with V at P. So so these might be maps from one manifold to another, but I can just these live in ambient spaces, and so F is actually going to be mapped from the ambient space to the ambient space, so I can just compute this sort of as I'm used to for regular Euclidean spaces. So another example of maybe this more exotic type of push forward is if F is a map from S2 to the reals given by X, Y, Z, just maps to Z. So here's my map, or here's my sphere, here's my real number line, and I just so I'll just draw some level sets basically. All these will go to, maybe I should draw them in different colors. All those points will go there, and all these orange points will go here, and the blue points will go here. So in this case, I can also think about what df does, and if you compute it, you'll see that basically whenever I have tangent vectors that sort of are parallel to the level sets, they'll go to nothing in the image under the differential, and then if I have a tangent vector that points like this way, it'll sort of go straight to R. The d by dz direction will be preserved. And then say if I have something that goes like that way, then it will, and only the d by dz direction gets preserved, right? So we'll get maybe something shorter. Okay, so next time, in the next video, we'll talk about what the relationship between this push forward idea is with differential forms.